Back 50 years ago, our founding father, Dr. Vern Sumi, actually put up the first demonstrational satellite. And his vision was, let's put observations that we can now do on the surface of the Earth. Why not put them up in the sky and look down? Because it's the clouds that move, and we want to be able to see those clouds moving. And he started us off. And his legacy lives on in all of us that are still doing research here. Since then, the program has evolved from these really big satellites, they're bus size, and then they got down to, maybe car size, which they are today. But the idea is that these are very big and bulky and heavy, and there's a lot of power needed to fuel them. So really, it's an economic decision that if we can use new technology that's available today to make, with lighter materials, better optics, better power sourcing, we can get these satellites down to the size of a breadbasket.
They are smaller, they're easier to launch, they're less expensive, so if we lose a few, you can just launch replacements. We still want the big satellites up there, the big buses, that are going to be up there for many, many years. But we also want to launch these smaller satellites so that we can have many, many of these satellites passing over the storms very quickly.
NASA has already decided that they are going to go to using these smaller platforms for as many of the different variables that we want to measure about the climate system as possible. And PREFIRE fits right in with that by demonstrating the technology, being one of the pioneering missions that actually will make measurements using this platform.
Probably the more important part of the Tropics mission is to demonstrate that a fleet of small satellites can do the job that in the past would have been done by a huge satellite the size of a minibus that costs $1 billion. So it's really important to have missions like Tropics that demonstrate that small satellites on a lower budget, on a more rapid development schedule, can still acquire the same data with the same quality that you could do in the past with huge, more expensive satellites.
So the Earth's energy cycle is pretty much driven by just two factors. It's the amount of sunlight that comes in and the amount of energy that the Earth emits back to space. And there should be a balance roughly between those two quantities. But the solar part tends to come in more in the tropics, which is why our tropics are warmer. And most of the emission tends to occur in the polar regions. And so what PREFIRE is going to do is it's going to basically map out that second portion of that energy balance. We're going to really try to understand how much energy is emitted from the polar regions, how much energy the atmosphere traps in the polar regions and keeps back into the Earth. And in doing that, we should be able to understand how the flow of energy between the tropics and the poles actually works and how that impacts the weather systems and the climate on Earth.
The Arctic is warming much faster than the global average. And the Greenland ice sheet, if it were to completely melt, would lead to 7.2 meters of sea level rise. Current observations of the Greenland ice sheet indicate that the edges of the ice sheet are undergoing rapid melting, but that the center of the ice sheet actually has a small net gain of mass. And this gain of mass is through the production of snowfall. So if we can better understand clouds and snowfall over the Greenland ice sheet, we can help inform and make more accurate predictions of future sea level rise.
So my research looks at air pollution, and I use computer models and satellite data, as well as measurements from ground-based networks around the world. Air pollution is the #1 environmental risk to human health. It's associated with shorter lifespans, with asthma attacks, with respiratory disease, and things like having even itchy eyes or sneezing. And some of the chemicals in the air we can see, like smoke from a forest fire, but many of the most dangerous chemicals are invisible to the human eye. So it's pretty cool that satellites can see these chemicals from outer space, even if we can't see them right at ground level with our own two eyes.
Those forecasts then can be used by regional planning offices, states, schools, particularly kids with asthma are very susceptible to ozone and aerosol pollution. We work both with the NASA scientists and the NASA satellite data, and we work with the NOAA more operational side of air quality predictions and how we might, again, use satellite data to help improve our understanding of what the air quality is today so that we can help better forecast it tomorrow.
Almost every time a new satellite is launched, we're like right there. We're like, either in the design process or in the processing process or in the storage. And it's just a very rewarding work to be working with this new data. You know, whenever a new idea comes along on how we can observe storms, we're right there. That is our legacy, and we're continuing that forward with these new missions.